Welcome to section 8.2, where we want to talk about just a couple nice properties of relations, some nice desirable properties, and that is reflexive, symmetric, and transitive. That's what we want to look at as far as these relations are concerned. So first, we'll define these three relations, and then we'll just work through like three examples to show you how to show these properties. So we'll start off with the definition. Let R be a relation on a set A, and we say R is reflexive if and only if for all x in the set A, x is related to x. This one might seem kind of silly. We're just talking about the fact that this element x is related to itself. R is symmetric if and only if for all x and y in A, x related to y implies that y is related to x. So this property of being symmetric, one quick example is something like, 1 is less than 2, 2 is less than 1. No, that's not true, right? So that less than the inequality that we talk about is not symmetric. Right? R is transitive if and only if for all x, y, and z in the set A. I'll give myself some more space down here. If x is related to y and y is related to z, then that implies that x is related to z. Again, think about something in terms of you have three elements. Let's talk about the less than inequality again. Right? 1 is less than 2, 2 is less than 3, and 1 is less than 3. Right? If our first element is 1, the middle element y is 2, and the last element is 3, 1 is definitely less than 3. So that less than inequality is transitive, but it's not symmetric because 1 less than 2 does not imply 2 is less than 1, so we fail to be symmetric. And of course, not reflexive because 1 less than 1, no, 1's not less than 1. But if you brought in the equality, 1 is less than or equal to 1, then all of a sudden now that becomes a relation that is reflexive. So these are the three properties that we want to study in this section, and we want to see if a relation that we define on a set is going to have any one of these three properties, or maybe all three of these properties, or maybe none of these properties. So we'll start off with a nice example where we can actually draw a directed graph, which we saw in the last section, 8.1. Since we're only talking about one set A, we can draw these nodes and draw a directed graph to see if we have this reflexivity, symmetry, or transitivity. So I'm going to say, for our first example, let's let the set A be a finite set 0, 1, 2, 3, and define R. And we'll use the set to define R. We have this relation, 0 is related to 0, 0 is related to 1, 0 is related to 3, 1 is related to 1, 1 is related to 0, 2 is related to 3, and 3 is related to 3. Right? This is These are all the elements that are in the relation R by definition. And now we want to ask the question, is this relation R reflexive? Is it symmetric? Is it transitive? So one way to do that, since it is a nice finite relation, we can show our solution by drawing a directed graph. So first, we draw a directed graph, which means our set A, these 4 elements, and again, your graph may differ, but since there's 4 elements, I think maybe I'll just put them in a square pattern here. Here's 0, here's 1, here's 2, here's 3. So there's our 4 elements from set A. Now when we look at the relation tells us how each element is related to another element in the set. For instance, for 0, 0, this ordered pair, that tells me that 0 is related to 0. So when we draw our directed graph, the element 0 corresponds through this relation back to the element 0. Then we have 0 is related to 1, so 0 is related to 1. 0 is related to 3, so 0 relates to 3. 1 to 1, 1 to 0, 2 to 3, and 3 to 3. So this is what our directed graph looks like. And these are the only elements in the relation, so I can't go drawing any more arrows that they don't give me. So our relation tells us that it looks like we have R as reflective because I have 0, 0, right? And by definition of reflexive, we need to show that each element relates to itself. Well, unfortunately for the element 2, it does not relate to itself. So R is not reflexive, namely because, and we really only need to give an example as to why, because 2 is not related to 2. We do not have this relation. Basically what happens is we're missing 2, 2 as an ordered pair in the relation. It's not there. So this is not reflexive. If it was there, this would be a reflexive relationship because every element would relate to itself. But because we're missing it, we can't say R is reflective. We could make it reflective if we put that there, but we're not allowed to just put it there because we want to. So it fails to be reflexive. Next, we want to look at symmetry. R is not symmetric because, and again, we just want to find an example to show why or why not. Now again, when we talk about symmetry, we have to look at the fact that this second piece that we see, 0 is related to 1, and 1 is related to 0. And by definition of symmetry, if I have 0 relates to 1, I need 1 to relate back to 0. Here I have 0 relates to 3, but 3 does not relate back to 0. Right? So it fails to be symmetric because it works one way, but it doesn't also have that backwards direction. So R is not symmetric because 0 is related to 3, but 3 is not related to 0. Right, so we fail there. You could pick another example here, like 2 relates to 3, but 3 doesn't relate back to 2. Right, so you can use that as another example. So it's missing 3, 0, right? 3 needs to relate back to 0. And it's also missing 3, 2. Right, if 2 relates to 3, then 3 needs to relate back to 2. All right, one thing to note is that Yeah, 3, 1 is also missing, but it's okay because 1 doesn't relate to 3, so we don't have to worry about 3 relating back to 1. Right? So you're saying, well, 3, 0 is not there, 3, 2 is not there. Isn't it also missing 3, 1? Right? It doesn't have 3, 0, it doesn't have 3, 2, it doesn't have 3, 1 either. But we don't care about 3, 1 because there is no 1, 3. 1 does not relate to 3. So we don't want to create 3 relating to 1 because then we would be missing 1 related to 3 as well. Right? So we just want to make sure that based on the relation, the way it's defined, how do we fix it? Well, that's how we would have to fix it. Right? I say fix it. We're not fixing anything. We're just saying yes or no to these. Next up is transitivity. R is not a transitive relation. Or just say R is not transitive because, and again, we just have to look for an example as to why not. Well, for transitivity, you have to go from one element to the second, and then the second element to the third. And if you have the first element to the third, then you have the transitive property. Right? If you can bypass that second element and get straight to the third, then you'd be fine. Notice that 1 relates to 0, and 0 relates to 3. Right? So we have specifically 1 relates to 0, and we have 0 relates to 3, but we do not have 1 relates to 3. So again, we're missing this. So it's not transitive because 1 relates to 0 and 0 relates to 3, but we don't have the direct 1 to 3. So we have 1R0, and we have 0R3, but 1 does not relate to 3. So I lose that transitivity. Again, go back and look at the definition. You need this and this to imply this, meaning X, R, Y, and Y, R, Z must imply X, R, Z. We don't have directly X to Z. In this case, they're specific numbers 1 and 3. So when you have this finite set, you can draw a directed graph to help kind of visualize, hey, is this thing going to be reflexive? Well, if I had that extra little 2 to 2 relation, I could say yes immediately. 0, 0, 1, 1, 2, 2, 3, 3, reflexive. But we don't have that simply because we're missing the 2 to 2 relationship. So on a general set, it takes on this more general meaning. But we've already used this stuff when we look at things like equality, like 2 equals 2. And then you can work that backwards, right? 2 equals 2. You're talking about a reflexive property, right? It's the property of equality when we talk about real numbers. But really what it is when you break the real numbers out into a set, an infinite set of real numbers, you can say that that set has the reflexive property because every real number is equal to itself. Right? So we call it equality because mostly we deal with multiply, divide, add, subtract. So we specifically deal with those operations and we give it a name equality. But really it's just the reflexive property that we're dealing with. So just to kind of look at that a little more in depth, let's say, second example, define a relation, and I hate to call it R, but R is the relation on R, the real numbers. Right? So this is fancy R, specifically the real numbers. R is just the relation, such that for all X, Y, and Z in R, X is related to Y if and only if X is equal to Y. Let's say we have this relationship where if we take 2 elements and they have the equality, then they're in that relationship. You can show that, in this case, the relationship, we're talking about the exact same element since we're boiling it down into the real numbers. The only way two real numbers are equal is if they're the same number. Right? But a nice thing to look at is, first, R, the relation itself, is reflexive. Because based on the way that this relation is defined, the x equals y, right, every real number is equal to itself. So it is in that relation. If I replace x equals x, well, yeah, for all x in the real numbers R. All right, so this definitely works for all real numbers you can find. R is also symmetric because if x is related to y, then y is related to x for all x and y in R, in our real numbers. Again, what does that mean? Well, that means that here, in the first one for reflexive, I'm just basically saying x equals x. Is that true? Yes, it's true for every x, so it is reflexive. In the second one here, now I'm saying, is it symmetric? Meaning, if x equals y, does that necessarily imply that y equals x? Yes, it does for every real number. Right? If you have this equality given to you, then you know you can flip that equality the other way. Right? If 3 equals 3, then 3 equals 3. You can say it backwards, right? Even though it sounds exactly the same. And then last but not least, R is transitive because if x is related to y and y is related to x, then, or sorry, y is related to z, I need to use that last one, z. If x relates to y and y relates to z, is this true? Yes, it is. Then x relates to z. Why? Because of this equality for all x, y, and z in R. So again, what that's asking is if x equals y and y equals z, does that imply that x equals z? Yeah, of course it does. Right, if these two are the same number, then this x is exactly equal to y, which means I can replace y with x, and I can skip y entirely. I can say that x and z must be the same. Right, and we've done this before in college algebra. You know, maybe we did it with functions. We had one function equal to some number, and then a completely different function equal to that same number. Well, that allowed us to just take the two functions and set them equal to each other. Right? If they have the same result, then I can set them equal to each other when we evaluate it at a given value or something like that. So again, we've probably encountered using this property before, but we've never exclusively called it the transitive property. And you can see that this set of the real numbers, this is an infinite set. I can't really draw a directed graph for this because it's an infinite set, and I don't want to write down an infinite list of numbers and start drawing arrows. Right? So that can get really, really cumbersome. So let's pick on a different relation. I'm going to pick on the congruence mod 5 relation. This one will have a little more meat to it. So we'll say let f be the congruence mod or modulo phi relation on the integers z. We'll say z to shorten things up. So we're talking about integers, positive, negative, whole numbers, and zero. That is to say, for all m and n in the integers z, m is related to n through f if and only if 5 divides m minus n. This is what we call the congruence mod 5 relation. It's basically a check for divisibility by 5. Are two elements of the set related in such a way that we can divide them by 5? Basically what they're asking. And then we just want to see, is f, the relation, reflexive, symmetric, or transitive? All three, maybe none, who knows, right? So first thing to start off is the reflexive property. Right, and what you want to do is you want to just ask yourself, if I take the same element and plug it in m minus m, right? So what we're asking is to show f is reflexive, we need to show, now you don't have to go writing me a formal proof, but I just want to see some good logical thought of this is why. So to show x is reflective, we need to show m, f, n. But remember, by definition, this is what the reflexive property asks for, is each element related to itself. So this relation means 5 divides m minus m, which implies 5 divides 0, right? Because m minus n is always going to be 0. It's the same element. But every number divides 0. Well, I mean, really, except 0, right? Maybe I'll say every non-zero number. Now we don't have to do parentheses. Every non-zero number divides 0. So 5 divides 0. Thus, m is related to n. Right, so no matter what number I pick, right, m and n are integers. Say you pick the integers where n is 7. 7 minus 7 is 0. Does 5 divide 0? Yeah, because 0 divided by 5 is 0. So 5 definitely divides 0 up. Take 0 divided up 5 times, you still get 0. So that is defined. So we do have this reflexive property. Thus, f is reflexive. And that's what we wanted to show. So we do get the reflexive property, which is very nice. For the symmetric property, again, similar argument here. You don't need to do a full-blown proof, but I need to see the logical thought. we want to show that F is symmetric. Or maybe come up with an example that shows it isn't. But we need to figure out first what we need to do and what we need to not do. To show F is symmetric, we need to show M, F, N implies N, F, M. All right, look at the definition of symmetry. If M relates to N, then N relates to M, gives us our symmetry. So in order to show that this is a symmetric relation, this is what we need. Now, if we have M, F, N, then do we get N, F, M? So this is a if-then statement. Does this imply this is what we need to show? So we're going to start by saying this is given. Does it imply this has to happen as well? So we'll say since M, F, N means 5 divides M minus N, we know that M minus N is equal to 5 times K. Right? If 5 divides this M minus N, then this must be a multiple of 5. That's the only way 5 can divide this number M minus N. And we're given that in order to show this. So we know that M minus N is a multiple of 5. We're going to say it's 5K for some integer K. However, this N minus M is what we need to show is divisible by 5. But N minus M is just the opposite of M minus N. Check it out. Positive N minus M, if I distribute negative M, negative negative is positive N. Positive N minus M, that is positive N and negative M, which is equal to negative 5K. We just said that M minus N, this quantity is 5K. Again, check it out, because if this M minus N is 5K, isn't the opposite of M minus N negative 5K? Yes, it is. It has to be, which is the same thing as 5 times negative K. Thus, 5 divides, since this is a multiple of 5, this is a multiple of 5, it's divisible by 5. So what we're doing is we're showing that the opposite ratio, yeah, it may give us a negative, but it still works. Right? If this is 10 minus 5, I get the result 5, and 5 divides 5. But if I flip those and say 5 minus 10, I get negative 5. 5 also divides negative 5. So that's all I'm doing. I'm just basically swapping the sign there to show that it's also a multiple of 5. It's just the opposite multiple of 5. Thus, F is symmetric. Just to summarize it all up. So again, we're dealing with integers, which is an infinite set. We need a more general way of arguing. Basically, it's a proof, when it all comes down to it. But it doesn't have to be so formal as a proof. Like in the last example, it wasn't a very formal proof. I'm going to give myself some space back, and then we'll hit up that transitive property. So last but not least, we want to ask, is F transitive? And again, To actually do this, to show f is transitive, to show it's not transitive, you just need to come up with a finite example. But to show it is transitive, we need to show that if m is related to n, and n is related to, let's use p, let's pick another letter, then given these two things, does this happen? Then is m related to p directly? Can I skip the n? Well, since m, f, n, and n, f, p are given, right, we're given that this happens and we need to show that the result is m, f, p. Well, since we have this, we have that 5 divides the difference m minus n, and 5 divides the difference n minus p. All right, and that's just coming from the definition of the relation that they gave us. Well, what does that mean for us? This means m minus n is equal to 5k for some integer k. To save some space, maybe I'll leave that out. And n minus p must also be a multiple of 5, because 5 has to divide it. But I don't want to reuse k again. I don't want to say that these two differences are the same 5k number. So I'll use 5l, where l is an integer. Again, I'll leave that out just to save a little space. Now here's the tricky part. We're looking for m minus p. Now m minus p is equal to m minus n plus n minus p. All right, see how I did that m minus p? That means I've got m minus n plus n, those are actually 0, minus p. All right, so there's a negative n and a positive n. But I can squeeze them back in there because they're not changing anything. All right, if I add n and subtract n, I just have to put them in the right way so that I can see these two numbers. But m minus n is 5k, a multiple of 5, plus n minus p is also a multiple of 5. Oh, sorry, I mean to write n minus p. I'm going to write 5l, which is equal to 5 times k plus l, which is 5 times some number, and look what we just got. M minus p, this quantity right now, is this number 5 times some other integer. K plus l is just another integer. So m minus p is a multiple of 5. If m minus p is a multiple of 5, this means 5 divides m minus p, and we're done. We just showed MFP. There it is. M and P fit my relation. They fit my relation perfectly. Thus, F is transitive. Right, so we can say yes to all 3 of these. And this is really nice. This is what we call a congruence relation. And you can do it with modular arithmetic. There's examples in the textbooks that have, show that congruence mod 2 is reflexive, symmetric, and transitive. It'd be pretty much the exact same process. So this is just so happens to be a really nice relation that we like to use as examples right off the bat. But if it's a finite example, Best way to do it is with a directed graph. Draw your arrows, see what you're missing, or if you have everything, then you can say yes. If you have an infinite set, then you have to go through a much more general approach, because then you have to show it for every number in the set, or every element in the set. It might not even be numbers, and then that obviously becomes a little more tricky. You need to get into proof writing. So that's really all I wanted to cover for section 8.2 are just these three nice properties that we have. So again, always go back to the definition to see what you really need to prove, right? Go back to the definition for reflexive. You're always looking to take the same two elements. I know I already erased it, but you're looking to take the same two elements, M, F, M, right? Same two elements. For symmetric, you are given MFN, and you need to show NFM, right? You need to show that the swap obeys that relation, and it's part of your relation. Again, a good counter example to that would be like the less than operation. You know, 1 is less than 2, 2 is less than 1? No, so it fails to be symmetric. And then, of course, for the transitivity, you have it right here. You're given these two things. You're actually given this and this, and you need to show that this actually holds true. Right? You need to show that you can basically omit this like two-step process to get from M to P, and can you just directly go from M to P? So work on some examples. You know, you'll see that just examples just like these. That's all you'll see on the study guide. I shortened it up a little bit. It's 1 through 13. I think like 11, 12, and 13, maybe 14 and 15 have the congruence relation stuff in it, like kind of like this problem. So if you have any questions, let me know. Otherwise, hang in there, and I'll see you in the next section, 8.3.